Now this is the first example. Okay, sorry, everything is like this really because my laptop went out that day. Now let me just read. Okay, an automobile component as shown in the figure, this figure, okay, is subjected to a tensile load of 160 kilonewton. So when you look at this question here, actually you can see both the forces are acting at the edges. Okay, so you can straight away apply the forces to be the same for each section. That means straight away you can apply forces to be the same at each section, or you can apply principle of superposition. Now I repeat once more, okay, the principle of superposition. So since it is two sections here of different cross section, so we can straight away split it up into two sections which I've drawn like that. Two sections which I've drawn like that. Okay, so just look at my laser pointer. Okay, just look at my laser pointer. Okay, so first take a look at this 160. So this is the first section AB. So if this is 160, so I just straight away take 160 directly, which is much easier. So if this is 160 for the equilibrium of section AB, this 160 here, which is acting towards the left, you must have another force acting at this end here, which is acting towards the right, which is also 160. So that the section, this part AB here, remains equilibrium. This is equilibrium. But originally, when you look at this section here in the diagram, it has no forces. It has no forces. That means zero forces acting here. Zero forces acting here. But then I have considered 160 here. So that means I must remove this 160 in order to get 0 here. So when I look at the second section, this green color section, this part here, okay, so since at this section B here, I have a force 160 acting towards the right, then when I reconsider the section B for the second part, okay, I have to consider the 160 on this section here, on the second part, has to be opposite in direction to this. So that I take this, when I take this 160, since it's opposite direction, is minus. So 160 minus 160, that means here will be 0. Okay, so at the second part, okay, then if I have 160 acting towards the right at section B, then I must have another force 160 acting towards the left at section C for the second part. So then this part here, BC, will be also in equilibrium. Okay, so that fulfill whatever that is given in the question, which is here at this end here, I have 160. So I have 160 here also. So the most important thing you have to check is the last part of your bar. Okay, you must have a force that is equals to the original force that is given in the diagram. So then you are safe. And second thing is, make sure that each part that you have considered, they are in equilibrium. And make sure that each section, okay, at each section, the net force, for example, the net force must be equals to whatever that is given in the question. For example, the net force here in the original diagram is 0. So that means at section B, the net force here also must be 0. If the net force here is 60 on the original diagram, if I have a net force of 60, then the net force at section B here also must be 60. Since this is 0 here now, so the net force must be 0. Okay, so once you have done this, that means you have found out the forces at each part. Then you can proceed by calculating the cross-sectional area of each part. So the cross-sectional area of AB is given as pi r squared. You can use pi d squared over 4, or you can use pi r squared. That is the cross-sectional area. Okay, the cross-sectional area of any circular section. So the diameter is 50 mm. So the radius is 25 mm, or 0.025 meter. So square times pi, so you get the cross-sectional area of section AB. Then you go for BC, the cross-sectional area of section BC. So this should be BC. Yeah? This is my mistake here again. Hold on for a while. Hold on for a second. Okay, so the area of section BC, that means this, the cross-sectional area, pi d squared over 4 or pi r squared, the same. So pi r squared or pi d squared over 4. So radius, whatever given here is the diameter, or 100 mm, so radius will be 50 mm, so into meter is 0.05. So you calculate the cross-sectional area, so you've got 7.854 times 10 to the power negative 3 meters square. You see, both is in meters square. Okay, then you can calculate the total deformation. Now the total deformation, the formula that we have is FL over AE. Okay, FL over AE, FL over AE. Why the force has been extracted out from this bracket here? Because it is common, and you can see part 1, part 2, the forces are the same. So that is why I extract the F here. Otherwise, your F will be with this FL1 over A1E1 plus FL2 over A2E2. Because sometimes the force might be different, yeah? It depends on whether, okay, at these intermediate sections here, you have any forces or not. Okay, so since it is 0, so that is why when I apply principle of superposition, and we have found that also, okay, that each part here, they have the same forces. So therefore that is why the force is common for both the section, and that is why I extract the F out from this main formula here. So now you can calculate the total deformation by considering a force 160 times 10 power 3, the length L1, so that is 90 mm. This is your part 1, yeah, 90 mm, so it's 0.09 for the length. The cross-sectional area of part 1, that is 1.963 times 10 power negative 3. The Young's modulus, okay, it's not given, Young's modulus here, sorry, hold on for a while.
I think it's given so you're the E, right?
Oh, yeah. Sorry. The E is given. Sorry. Different material. Thank you, Faisal. Thank you. Thank you. You have been paying attention. Very good. Okay. So, sorry, it's given here. E for the first part, which is made up of steel. E for the first part is 200. And then the E, the Young's modulus for the second part is 80 gigapascal. Okay. 80. Okay. So when you look at this formula here, E1, E2, okay, sometimes if let's say they are made out of same material, that means if same material, they will give you only one E, okay? Since both different materials, and you have E1 and E2. Okay, so put in your F, L, the length, the area, and the Young's modulus. Remember, this Young's modulus here is given in gigapascal. That is also equals to giganewton per meter squared. Giganewton per meter squared. So that is why all the area I convert it to in terms of meter, and the length that I use also must be in terms of meter. Okay, so that is the values when you have substituted into the formula. So you got this, and then you can find out the total deformation in meter. Okay, that is for the first example for this section. Okay,